So we'll start with the first problem, that's finding the shortest path using Dijkstra's algorithm. So the Dijkstra's algorithm starts by saying you have a source vertex, you want to find the shortest distance to every other vertex. We also assume that all the edge weights are greater than or equal to 0. So when you apply the Dijkstra's algorithm, at the end of the algorithm, you will have distance to, that is the distance from A to all the other vertices, and the edge to, and which edge was used to do that vertex. So let's go back and look at what the Dijkstra's algorithm means. So the main idea of Dijkstra's algorithm is to place all the nodes. First of all, we're going to create a minimum priority queue, and then you initialize all the distances to infinity, and the only thing is that the distance to 0, s from s to s, would be 0. And then we insert s to the priority queue with the distance while it's not empty, so the priority queue will run n times number of vertices. You delete the minimum, and then you find all the adjacency entries, adjacency edges to that, or adjacency vertices to that vertex v, and then you relax the edge. What do we mean by relax the edge? Relax the edge means that this idea here. So suppose we already have some distance to w. Let's assume it's 20. We also have some distance to v. Let's assume that's 10. So these are the shortest distances you have found so far. Let's assume the edge weight is 2. So now we know that using the distance to v, you might be able to get a better distance. So this can be 12. So that's the idea of relaxing the edge. So from a code perspective, what we do is we take the distance to v, which is 10, and then add the weight, which is 2. And because the total 12 was less than the best distance we have, which is 20, then what we're going to do is we're going to adjust the distance to w to 12. And then edge would be the new one. And if the priority queue contains w, so w is still there, right? If it contains w, what we're going to do is we're going to decrease the key, so it's possible that that entry can go up the priority queue because it got a new distance now. If it's a new one, then we're going to insert it to the priority queue. So let's apply that principle, same thing, to our problem. So here's our problem. So what we're going to do is we're going to assume that we know that distance from our source vertex is a, so distance from a to a is 0. And using these edges, we can update the distances to b to be 3, distance to c to be 6, and distance to d to be 2. And we also know that edge came from a at the moment. We might change that. So this means that we relaxed this vertex. That means that vertex is taken out of the priority queue, and 3 new vertices were put into the priority queue. Now we're going to look for the next smaller thing in the priority queue, which happens to be d. So from d, we have 2 vertices, 2 edges going out, in fact 3. So if you look at the edge dc, that can actually give us a better distance, which is 5, 2, and 3. So this could change to 5, and this will change to d, because that came from d. And now if you look at this one here, we didn't have a distance to e, so now we get a new distance, which is 2 plus 8, that would be 10, where that came from d. If you look at this one, we didn't have a distance to g, so now we get a new distance of 9 that also came from d. So we considered those 2 edges, and we're done with d. So d is taken out of the priority queue. Now we can take the next smaller thing from the priority queue, which turns out to be this, b. And so from B, we are trying to relax some edges. So let's see whether we can get a better distance to E. Now, E has a distance of 10 right now, but I can get a distance of 9 through B. So I'm going to change this to 9. Say edge came from B. And that's all I can do with the B. And now I'm going to take the next smaller thing, which is, so we have 5, 9, 9. So I'm going to take this one here, which is C with 5. So I'll look at this edge here. So with that edge, because C is 5 plus 4 is 9, I can go to E 9, but I already have 9, so I'm not going to change that. So I'm done with C. Then I'm going to take the next available one. Depends on the implementation of the priority queue. One of them is going to be at the top. So I'm just going to pick up E equals 9. With that 9, I will be able to change F now. So F would be 11, and the edge came from E. Now what we're going to do is, and that's all I can do because that's the only edge, and then we take the next thing out of the priority queue, and we try to do what we can. So G has two things. If I use G, already has a 9 plus 2, 11, but I already have 11 for F. E is already relaxed, so I will not use this one. And so essentially I'm done with the problem. So at the end, we are getting the following final distances. So for A, the shortest distance from A to A is 0, A to B is 3, A to C is 5, A to D is 2, A to E is 9, A to G is going to be 9, and A to F is going to be 11. So now, what is the shortest path tree looks like? So I can color the shortest path tree like this. So AB is an edge in the shortest path tree. So here's one of the edges, and DC is an edge. So DC is an edge, and AD is an edge. AD is an edge, and BE is an edge. BE is an edge. That's the BE, and then EF is an edge. EF is an edge. So let's color EF, and then DG is an edge. DG is an edge. So let's color DG. Oops, no, that's not the DG. This one is the DG. All right, so that shows the shortest path tree and the shortest distances. All right, so one of the cool things that I wanted to show you in class was that this very cool application we developed when I was at Carnegie Mellon. So in the application, it was part of a pen-based computing course. So let's draw. Notice that as I draw things on the smart paper, it recognizes the shapes and then convert them to the nodes. I can label the nodes, and I can also draw edges the same way we have in the first problem. Currently, it's giving a default weight of 10 to all the edges, but I will go and change it once I'm done drawing the edges. So here are the edges, and we have this, and then I have this edge here. So those are the edges that was in the current, the problem. So I'm going to change this to 3 as in the problem, this to 6. Notice that it's recognizing my handwriting and making the changes. So that's a 4, and that's a 8, and this will be a 3, this will be a 2, this will be a 2, and this will be a 7, and this is a 3, and a 2, and a 6. So now we have an undirected graph, but I can still apply Dijkstra's algorithm. Now the answers I get here might be slightly different because I have an undirected graph, so this means that you can go both ways, and therefore you may not get the same distances that we got when solving the problem, which was a directed graph. So when I apply the Dijkstra's algorithm, It's going to work like this. Put the 0 into the priority queue, and notice that the colored vertices are in the priority queue. The blue ones are already relaxed and they've taken out of the priority queue. That means we have found the best distances to those blue vertices. So we already know this is best distance is 3, this is 2, this is 4 now. So as we get blue nodes, that means they've been relaxed. This is 9. So let's see what happens here. So it keeps working. So this is 8. I found that. And then this would be, destination node found. So it found the right path. So if you look at the shortest path from this to that, that would be 3, 1, 4, 4. It's 8 plus 2, 10. So that's the shortest distance from this to that. The shortest distance from this to that would be 9. So that's an interesting application of Dijkstra's algorithm. If you are curious about these kind of things, we do these type of things in independent projects to do sketch recognition and building models and applying algorithmic things. These are like smart papers, so you can create smart graph paper or smart chemistry paper or smart physics paper and pretty much draw anything and animate it. Okay, now let's take a look at the exercise 1b. This is also related to Dijkstra's algorithm. In this problem, we're given a digraph of 8 vertices, but we do not know the actual graph. So what we have is the distance to an edge to array after the vertex 4 has been relaxed. So this was the last thing that was relaxed. So this means that anything that came before that must have been relaxed before that. So this is the distance to 10. Now, since in Dijkstra's algorithm, we relax vertices in the order of the distance from A, you can imagine that, or you can assume that everything less than 10 would have been relaxed before that. So how do we find the answers to the following questions? So the first question is, based on the table above, which one is the source vertex? I think that's quite easy to know, which is 3, which has a distance 0. So I'm going to write the answer 3. Give the order in which the first 5 vertices were deleted from the priority queue and relaxed. So obviously 3 is the first vertex to be released. And then you look for the next smaller thing, which is going to be 5. And then you look for the next smaller thing. That's going to be, I believe it's 7. So that's vertex 1. And the next smaller thing is going to be 8. That's going to be vertex 7. And then finally, we just relax the vertex 4. So this means that vertex 4 is the other one. So is it possible to know the next vertex that will be relaxed and why? Yes, it is possible, because the next vertex that will be relaxed would be this one here. Because now we know that 4 is already been relaxed and there will not be any more changes to 6. So the next vertex would be 6. So it says that draw using edge to and distance to arrays to draw the shortest path tree generated from the source vertex. So let's take a look at that. And so what we're going to do is we're going to draw the shortest path. So obviously we're going to start with A, source vertex. And let's take a look at some of the smaller ones first. So we have here distance 3 to 5. So there's an edge from, the first source vertex is 3. And so there's an edge from 3 to 5. And that has a distance of 3. So there's the distance 3. And if you look at the next one, which is 7, there's an edge from 5 to 1. So this means 5 to 1. So there's an edge from 5 to 1 with a total distance of 7. So that's the distance from 3, which is the source vertex here. So this means this got to be distance 4. We look at the next one, 8. So the 8 came from 3. So there's an edge to 7 from 3 So h2 7 from 3, which has a distance of 8. And then the next one is 10. So 10 came from 7. So there's an edge from 7 to 4. So there's an edge from 7 to 4 with a total distance of 10. We already have 2, so this got to be 2. I mean, we already have 8, so this got to be 2. And then the next thing we know is that, I think that's 10. So the next one is 12. So there's an edge from 1 to 6. 1 to 6. 1 to 6. And which is 12. So this means 3 plus 4 plus 5. So we have that. Now we don't really know. We probably know that this will be relaxed next because there's no other way to get that shortened. So this will be at the top of the priority queue now. So this should be the shortest path tree that we know so far. Okay, so the next problem we plan to do is the Bellman-Ford algorithm. So in the Bellman-Ford algorithm, you're going to go through all the vertices, and then you're going to go through all the edges and relax these edges. So this inner two loops will run E times, and the outer loop run V times. So in the worst case, the Bellman-Ford algorithm is V times E. So let's talk about the notion called pass I and how that works. So let's take a look at this problem that we were trying to solve. So in the preset page, that may have been +1, but let me put this to be -1. It doesn't matter. You can put 1 if you like. So let's work it out and see what happens. So in the Bellman-Ford algorithm, it says show that Dijkstra's algorithm fails to find the shortest path tree starting from source vertex D. So if you start from short vertex D, so you're going to put these things into the priority queue. That would be 0, and this is 1 because I'm relaxing these edges. And this would be -1. Now, the next thing now, because you have now in the priority queue these 3 vertices, and you're going to be taking A out. But as you can see, there's a shorter path to A through this. That would be -2. So the Dijkstra's actually fail because we have already taken A out, thinking A is -1, and we will never apply, never relax A again. So that's the problem with applying Dijkstra's algorithm when you have negative weights. So let's apply the Bellman-Ford algorithm to see what to do here. So in the Bellman-Ford algorithm, let me just erase this that I wrote here and take a look at what we will do. So in the pass 1, what you do is you start from D, and these are zeros, and E hasn't been touched. So we have C, we can relax C, which is 0, and then we can relax B, that's going to be 1, and we can relax, what was the other one relax? Yeah, we can relax A, that's going to be -1. And the second pass, we're going to be relaxing B again. So can we get a better distance to B? Yes, we can get -1, so we can change this to -1. So notice that the pass 2 means I'm considering paths of length 2. In the path 1, I consider paths of length 1. Now I'm considering paths of length 2. So if I take path of length 2 from D, D, C, B is 1, then we can have D, B, A. Let's see, it gives a better one now because it gives you 1 plus -1, so I'm not relaxing that because I already have a better one, -1 here. The other path 2 ones are this to that, so D, A, E. In that case, I get a new number for E, that would be -2. And now that pass 3. Pass 3 means I'm going to be relaxing with paths of length 3. So let's take a look at paths of length 3 from D. So we have 1, 2, 3. So that means, yes, I can relax A now with -2. So A is now -2. Let's take a look at other path 3. So D, so that's 1, 0, -1. But I already have -2, so that's okay. I believe that's there's also another path here, D, C, like that. That's 0, 0, -1. But I already had -2, so that's not going to work. So that's pass 3. So if you look at pass 4 is if we don't have to do it here, but pass 4 is that you're looking for paths of length 4. But there are no paths of length 4. Actually, there is one. So D, C, B, A, E. So let's see what happens. That's -1, -1, -1. Yes, so that's going to be -3. So the E can be relaxed to -3 if you go through the paths of length 3. So that's the pass 4. I don't believe there's any other paths of length 4 here. So the final answers that we retain are these for the distances from D. Those are the distances. Now note that we have 5 vertices, and in order to make sure that we relax all of them, we have to do it 4 times, 5 minus 1. So, but it's possible that you may not relax anything when you go through a certain pass, and therefore you are done. So that's the Bellman-Ford algorithm and how you apply it. Okay, so exercise 2 was about DAGs, or directed acyclic graphs. Now we have, if you have a directed acyclic graph, we can find the shortest path using a topological sort idea. That means we find the topological sort and we go in that order and try to relax things. So what do we mean by that? For example, if you have, let's say, 4 vertices, so A, B, C, D, and here's a here's a topological sort for that. So let's take something like this. And if I knew the distances, so let's say this has -1, this is 2, and this one is 1, this one is 1, this one is 0. So if I keep relaxing these things using the topological sort, what I'm going to do is I'm going to say using this edge, I can say B is a 2. Now, using this edge, I can say C is a 2. And using this edge, I can say B. Now C can be 1, so C can be relaxed more because I can get to 2 and then so this can be 1. Using this edge, I can only get to 3. That's not good enough. Using this edge, I can get to D, so I can get to B in 2 plus 0, so the D would be also 2. So now let's see whether I can get better. Using this edge, I can say 1 plus 1 is 2, but I already have a 2. So I have used all the edges in this graph, and I have tried to relax it there. So I have found the shortest distances from A to all the other vertices using the topological sort algorithm. Now, how can one apply that to this problem here? So instead of 2 here, I'm going to write the 2 in here. So instead of 4 here, I'm going to write the 4 here. And same thing with 1. Same thing with 3. So what that means is I can get to this using this edge. I can get to this in 2. And using this edge, I can get to this in 2. Using this edge, I can get to this in 4, but I already have, so if I consider these edges in that order, so I'm not going to change that because I already have a 2 here. This one already have a 2, so I'm not going to change it. 4, yes, I can improve that because right now I'd have infinity, so I did that. So with this one here, I have a 1, so therefore I can improve this to be 1 using that edge. And then using this edge, yes, I have a 4, but I could improve that to be 1. And this one is 1 using this edge here. If I use this edge, I can get to 3, but I already have a 1, so I'm done with that. Using this edge, I can do 3, but I already have a 1, so therefore I have finalized the shortest distances to this here. Now then you can continue this idea, so you can distribute these weights into the edges and say with that, now this could be 3, 2 plus 1. And with this one, this could be 3, 2 plus 1. And now can we do better? Well, I guess, these things are 3 now. I cannot do better because it's 1 here plus 3, 4, but I already have a 3 and so on. So the idea is to continue this idea, continue this algorithm until we obtain the shortest path from top to the bottom. So whatever the shortest path you find here, the shortest distance, that would be the path that will give you the distance. So you'll have to think about a specific algorithm to do it, but without actually explicitly building the graph.